Hello guys, thank you so much for being with me in another artificial neural network tutorial video. Previously the score function was a linear function, and now we say that the function can be more complex and non-linear. Here we have first multiplied the w1 parameters in the input and applied a non-linear function to this product instead of calculating the scores directly from the input features themselves. And now we have done this calculation from their linear combination with w1 parameters. These points are still the scores. These scores actually are still the scores belonging to the classes. If our neural network is more than 2 layers, it will not make much difference. As the layers increase, we check higher level features to detect the input belonging to the classes. For example, instead of recognizing the raw pixels in the image, we perform the classification based on the lines or simple geometric shapes or the texture of the image. The neural network with 2 layers can be implemented with 11 lines in Python. SYN matrices are the same weights or synapses here. We said that we can implement this ourselves. First, we do the forward step by multiplying x by w and a nonlinear transition. We get the higher level features h, and now we calculate the scores based on this h. There is no need for nonlinear transformation. Then we can calculate the loss from these points, these scores. The higher this loss is, the worse this algorithm and weights are. We are looking for less loss. Now that we have completed the forward stage, it is time for the backward stage. The score here means the differential of the loss function compared to in respect to the scores. We calculate the gradients with the help of the chain rule. Now that we have these gradients, it is enough to update the parameters. We said that the idea of neural networks came from the brain, but as much as we have simplified these brain neurons, there is no more similarity between natural and artificial neural networks. In neural networks, the output of each neuron is not directly connected to the input of the next neuron. In between, there is a distance called a synaptic distance in the modeling we have done in artificial neural networks. We have simulated this distance with weights. The brain normally has 10 to the 11th power of neurons. We cannot produce so many neurons. The idea is to create a network of these neurons that has the same function as the brain. Here you can see the sigmoid activity function that approaches 1 asymptotically at large x's and asymptotically approaches 0 at very small x's. Historically, this function has been used a lot, but now we know that there are better functions. It is better for us to do the calculations at the layer level instead of the neural level. There are various activity functions. The hyperbolic tangent function is like the sigmoid function, only it is in the interval of -1 and +1. The ReLU function itself has different types. For example, a leaky ReLU function is introduced to avoid a zero slope. In places where the slope is 0, learning does not take place. We have said that all our calculations must be differentiable, so that we don't get into trouble in the backward stage. So with this curve making trick, which you can see in the figure, with blue color, we can also solve this problem of non-differentiability. Now that we know that what a neural network is, we can show it as an architecture. We have an input layer and an output layer. In the hidden layer, we have a number of high-level features. You can see that in each previous layer, each neuron is fully connected to all neurons in the next layer. These are called fully connected neural networks. In this slide, you can see the implementation of a single neuron. But we said that our preference is a layer-by-layer implementation. In this piece of code that shows the layer-by-layer implementation, first we have defined the activity function of the layers. Then we have randomly generated the inputs from the normal distribution. We have generated numbers close to 0. This activity function is applied to the sum of the bias with the dot product of the input vector and the weights vector. We implement forward calculations layer by layer. We implement each layer with one line of code. The implementation of the forward step is very simple. The number of inputs in these implementations is known. For example, when we are solving the Seyfarth problem, the inputs are 3072 neurons. The number of outputs is also known. For example, in the Seyfarth problem, we have 10 classes, but the number of layers and the number of neurons in each layer are unknown, and we have to determine them. In the first figure, we have 3 hidden neurons. The red area means that any new data that enters the problem after this modeling, if it is placed in this area, it will be classified as red. And the green area also means that this new data will be classified as green if placed in the green area. You can see that this model did not perform well even on the training data set itself. If we increase the number of neurons, the error on the classification of the training data set will decrease. By increasing the number of neurons, we can make the function more complicated. By increasing the number of neurons, this function will become too complicated. No human agent will also consider the decision boundary. Our goal is to correctly classify a new data entry. This model is complicated to such an extent that despite the very correct and accurate classification of the training data set, it does not have a good ability to correctly classify new data. We call this problem overfit. Anyone who works in the world of machine learning faces this problem and must know how to solve it. Overfitting is a condition where the accuracy on the training data set is very good, not necessarily 100%, but the accuracy on the new data is not good. It has poor generalizability. We can interpret that the data of the training set has been preserved by the model, has been actually memorized by the model. We want to classify the data of the training set well and have a good generalization ability on new data. From machine learning, there is a principle called Occam's principle. This principle says that if you have two different hypotheses, both of which are equally good and have adequate accuracy on the data of the training set, the stronger hypothesis is preferable. The hypothesis is the boundary of decision making. Why do we prefer the simpler hypothesis? Intuitively, because the simpler hypothesis will perform better on new data. This is the Likiralu, which I talked about for you. these are the activation functions, like the more complex a hypothesis is, the more likely it is to be wrong. And now, how can you face this overfit? Let me. Okay. We have already told the solution. We have explained a method. There are other methods. We had two sections in the loss function. One part was data loss, where the emphasis is on learning well from the training data set. Another part is regularization loss, which will improve performance when facing new data. Our goal is both sentences. The smaller the coefficient of lambda is, the importance of regularization loss decreases compared to data loss. That is, our model learns the data of the training set well, but it will not perform well for new data. The larger this coefficient is, the more important regularization loss is compared to data loss. That is, our model is supposed to perform properly on new data without learning the data of the training set. This is not possible. This lambda is a hyperparameter. Determining the value of this hyperparameter is very important, and no one will tell us the right value. One of the solutions to determine this optimal value for hyperparameter is cross-validation. You may think that since the increase in the number of neurons did not cause the problem and overfit, then we can prevent the occurrence of overfit by reducing the number of neurons. This is wrong, because by reducing the number of neurons, we reduce the power of the neural network. Instead, we should use a stronger regularization to have a strong neural network and not get involved with overfit. In order to understand whether the decision boundary is suitable and the complexity of the function is good or not, you can consider a hypothetical decision boundary for training data in your mind, which can perform well on new data. We will mention more methods for regularization. So far, we have introduced neural networks and said that what we know as a neural network is a layered architecture, which is much more efficient. This layered architecture requires less time to perform tasks. We said that these artificial neural networks are to some extent simpler models of neural networks, which cannot be considered as a proper simulation of the neural networks of the human brain. We said that the bigger the neural network, the more complex problems can be solved by it, and we use regularization to solve the overfit problem. We have currently studied stochastic gradient descent among various gradient descent algorithms and other optimization methods. We said that depending on the problem, any of these methods may be suitable. We want to talk a little about the activity functions. The activity functions of neural network layers. We said that simple functions and linear classifiers perform well in very simple problems. But in the real world, things are not that simple. For more complex problems, more complex functions are needed. As you know, sigmoid, hyperbolic tangent, and the activity functions have been introduced for this purpose for a long time. As you can see, hyperbolic and sigmoid the sigmoid function and hyperbolic tangent function are very similar, and they can be calculated from each other. The ReL function itself has many similar and related functions like parametric ReLU, leaky ReLU, and we said that in order for ReLU to be differentiable at all points, it should be smoothed a little. For this, we use the exponential or ELU function. Until a few years ago, the function that most people used as the activity function in neural networks was the sigmoid function, which is also called softmax or logistic. It was very popular until a few years ago, but now it cannot be described at all. This function has advantages and disadvantages. For example, one of the advantages of this function is differentiability at all points, but one of its disadvantages is that in areas more than +1 and less than -1, the slope is 0 and the learning does not take place. These areas are called saturated areas, and no matter how much time you spend on training, neurons will not be trained. When backward, for example, at x is equal to -10, which is a zero slope, the gradient of the loss function is in relation to respect to x will be almost 0. At the point x is equal to 0 itself, there is a good slope. The value of this slope is 0.25, which is a good number, and the highest slope is at this point. So we have no problem at this point. But in saturated areas, the local gradient is 0. Then the gradient becomes 0 with respect to the input. Practically, it means that no recovery happens. The second problem with the sigmoid function is that its output is always between 0 and 1. That is the average, the mean output of this function will not be 0. The output of this function is actually the output of the neuron that uses this function as an activity function. During backward, when we want to calculate the local gradient with respect to parameter w, we use the chain rule, and thus we need the differential of the activity function with respect to parameter w. The activity function is a sigmoid of w parameters. For this, the partial differential of sigmoid with respect to w should be calculated, and we're talking about these slides actually. The partial differential of sigmoid with respect to intermediate function like g should be calculated, and the resulting dimension of the differential of g with respect to w should be calculated. If the neural inputs are all positive, then the gradients are positive during backward. Assume that the inputs to the neuron are all positive, because these inputs are the outputs of another neuron with a sigmoid activity function. The output of this function is always positive. With this account, progress and movement will be only in the positive direction. It means we always move in the same direction. Now, if we multiply everything by negative, we can only move towards a negative. So finally, we have to take a zigzag route. This zigzag path wastes time and will require more repetitions, whereas if the averages were 0, there was no need to spend this extra time. The third drawback of the sigmoid function is the time-consuming act of the operation of exponentiation that exists in this function. When there are millions of neurons in each neural network in the real world, this time-consuming becomes more problematic. One of the defects can be solved very easily, and that problem is that the averages are not 0. The hyperbolic tangent function was introduced for this purpose. However, there are still other defects in these activity functions. Have a nice time.